Welcome to This Explainer. Today, we're taking something that honestly often feels incredibly abstract and, let's face it, a bit dry, logical reasoning, and we're going to transform it into something completely visual. I mean, if you've ever found yourself lost in a maze of complex arguments, well, visual logic is essentially your map out of there.
So think about this. How do we actually prove an argument? It's one thing to confidently state that something is true, or, use flashy persuasive rhetoric to win over a crowd, but rhetoric relies on emotion and phrasing. Logic, it requires mechanical proof. How do you visually demonstrate that a conclusion absolutely must follow from the facts presented? How do we systematically ensure we aren't just making a giant leap of faith? Well, that exact challenge is the puzzle we're unlocking today. We're going to see how replacing words with spatial boundaries literally forces arguments to prove themselves. It's pretty amazing.
Okay, here's our roadmap for today. We'll start with visualizing abstract logic, then move on to simple sets in Socrates, explore complex arguments in practice, and finally, we'll wrap up with the power of visual reasoning.
All right, let's jump right into Section 1, Visualizing Abstract Logic. So when we talk about a Venn diagram, we're talking about a rigorous logical tool. Its main job, clarifying whether premises actually support a conclusion. It does this by showing the exact boundaries and relationships between different sets of info, basically creating a physical map of abstract ideas. Now, when John Venn originally popularized this method back in the late 19th century, he was building on Boolean logic to create a standardized way to visually represent propositions. By assigning a geometric shape, usually a circle, to a specific class of things, we translate those abstract categorical statements into an actual spatial reality. The overlapping boundaries literally force the logic out into the open. It maps out inclusion and exclusion, completely eliminating the ambiguity that language so often hides.
Moving right along to Section 2, Simple Sets and Socrates.
Let's see how this visual framework builds a classic syllogism, using literally the most famous logical sequence in history. Step 1, all men are mortal. Step 2, Socrates is a man. Step 3, therefore Socrates is mortal. If we want to test this out, we start by drawing a large circle representing the broad category of all mortals. Inside that big circle, we drop in a smaller circle representing men, because, well, our first premise dictates that the entire set of men is completely contained within the set of mortals, right? Then we hit the second premise. Socrates isn't a broad category, he's a single specific entity. So we place that single data point right inside the men's circle. And because the men's circle is already locked entirely inside that mortal boundary, our Socrates data point is unavoidably trapped inside mortals too. The conclusion's validity is undeniably confirmed by pure spatial necessity. You just can't argue with the geometry.
Now for Section 3, Complex Arguments in Practice. Let's compare a simple, classic premise with a totally modern workplace scenario. On one hand, we have a clean, absolute category. Socrates is a man. It's an all-or-nothing proposition, which is absolutely perfect for concentric circles, where one is fully swallowed by another. But look at the complex premise. Some data analysts are Python users. Modern organizational scenarios rarely deal in absolutes like ancient philosophy did. They involve overlapping groups of employees, completely different skill sets, and partial intersections. We aren't saying all data analysts use Python, and we definitely aren't saying all Python users are data analysts. We're simply asserting that a shared space exists between these two distinct sets, and that requires a much more nuanced visual model.
To sort out these partial relationships, we just extend our method to multiple interlocking circles. Imagine 3 overlapping sets: data analysts, Python users, and remote employees. When we draw 3 intersecting circles, we create these really distinct, segregated zones. The exact center, where all 3 circles overlap, represents the specific subset of remote data analysts who use Python. The petal-shaped intersections between just 2 circles, those represent people who share 2 traits but not the third. By visualizing these partial intersections, we can systematically test complex statements against our established facts. So if a manager claims all of our remote data analysts use Python, we can just check the diagram. We look at the intersection between remote employees and data analysts. If any part of that intersection falls outside the Python user circle, boom, the manager's claim is logically invalid. It takes a confusing, multivariable word problem and turns it into a precise, easy-to-read geometric test.
Which brings us to Section 4, the power of visual reasoning.
So why do we use this? Well, this visual framework gives us 3 huge core strengths. First up, it rigorously tests validity. It actually demands that conclusions necessarily follow premises by giving them literally no physical place else to exist within the diagram. Second, it exposes contradictions instantly. Let's say premise A structurally requires a specific overlapping region to be entirely empty, but premise B introduces a data point that has to reside in that exact same region. Well, you now have immediate visual proof of a logical contradiction. You don't have to argue semantics, you literally just look at the map. And third, it simplifies complex reasoning. Our brains process spatial relationships incredibly efficiently. So, by mapping propositions to areas, we completely offload the cognitive burden of trying to hold multiple, conflicting sentences in our heads. It makes abstract logic totally accessible and actionable.
Now, in formal academic logic, Venn diagrams are especially vital for visualizing what logicians call mood and figure in categorical syllogisms. I know, fancy words, but mood and figure basically just dictate the exact structure of an argument. This visual logic ensures that universal affirmatives, statements like all S are P, are represented by shading out the region of S that falls outside of P, essentially declaring that space conceptually empty. Universal negatives, like no S are P, shade out the intersection entirely. And particulars, statements like some S are P, require the precise placement of an X right inside the intersection to show that at least one subject actually exists in that space. This rigorous methodology leaves absolutely zero room for misinterpreting the structural demands of formal logic. It forces strict adherence to the exact technical claims being made. As our source material so perfectly puts it, in this system, validity is not just asserted, but demonstrated. A Venn diagram beautifully bridges symbolic logic with intuitive spatial understanding. It proves that truth has to be visually proven, not merely spoken with authority. When you use this framework, validity isn't just claimed by whoever has the loudest voice in the room. It is mechanically and undeniably demonstrated right there on the page, built on an unshakable geometric foundation. So, let me leave you with this. Where in your own life could you apply visual logic to expose a contradiction? Whether you're listening to a complex political debate, evaluating the structural soundness of a business proposal, or maybe just trying to unpack a tangled argument with a friend, consider how mapping the sets might actually cut through the rhetoric and reveal the actual truth. Try drawing it out next time. Honestly, you might be profoundly surprised with what the boundaries show you. Thanks for joining me on this explainer.